if you type how to exit Vim into a traditional relational database, it basically just deterministically scans for the exact string, EXIT.
Right,
But
exactly.
like if you throw that same query into a modern AI semantic search, it actually understands your panic. It knows you're trapped. It understands the underlying intent of those frantic keystrokes.
Yeah, that jump from deterministic string matching to these probabilistic high-dimensional vector spaces, it fundamentally changes how we interact with data.
Totally.
I mean, it forces developers to stop thinking about exact matches and, well, start thinking about geometric proximity.
Welcome to the deep dive. It is late. You've probably got your IDE set to dark mode, maybe a lukewarm coffee on your desk, and you're trying to map out how the back end of search is actually being engineered today.
Which is a massive topic.
It is. So today, we're opening up a stack of technical architecture notes on modern retrieval systems. And our mission here is to really deconstruct the exact mechanics of building a search app using vectors.
Yeah, we aren't looking at the flashy front-end chatbots today.
No, not at all. We are digging into the data pipelines, the math, and, the underlying architecture that actually makes these systems intelligent.
Because honestly, that's where the actual enterprise value is currently being built. I mean, text generation is great for a demo.
Oh, sure, it looks great.
But if the underlying model can't accurately retrieve the correct proprietary data to ground its answers, the entire application just collapses into hallucination.
Right, it's useless. So let's start at the absolute baseline of this architecture shift, which is getting away from keyword matching. Because software engineers are incredibly comfortable with SQL, right?
Oh yeah.
You write a query, it finds the row, it returns the data, it's binary. But semantic search introduces embeddings. It converts text into vectors.
Right, and to visualize this mechanically, we really have to stop thinking about organizing a database by alphabetical strings. We are mapping out a massive, multi-dimensional geometric space.
Okay, so like an analogy here. It's sort of like organizing a massive library, not by the alphabetical titles of the books, but by the vibe.
The vibe.
Yeah, like the core meaning of the stories. So that even if two books use totally different words, they sit on the exact same shelf because mathematically they mean the same thing.
That's actually a great way to put it. And the mechanism driving that clustering is what developers really need to internalize. An embedding model is basically a neural network that processes text and outputs a dense array of floating point numbers.
It's like 768 or 1536 dimensions.
Exactly. And when a user submits a query, that query is also run through the same model, generating its own coordinate array.
Yeah.
Then the system just calculates the distance between the query vector and the document vectors.
Using cosine similarity, usually, right?
Frequently cosine similarity, yes. It measures the angle between two vectors. If the angle is very small, the cosine similarity is close to 1, meaning the semantic relationship is incredibly tight.
So if I search for golden retriever, the coordinate for that query is mathematically adjacent to documents containing canine or dog,
Yep.
even if the specific string golden retriever never appears in the text.
Precisely. The system isn't reading between the lines. It's calculating the geometry of the intent.
Okay, but here's the immediate bottleneck when you actually try to engineer this. How do you map a massive, like 500-page enterprise technical spec document into that geometric space?
You can't.
Right. You can't just pass an entire PDF through an embedding model. I mean, context window limitations aside, the math itself would just break down, wouldn't it?
Oh, completely. The resulting vector would be totally useless. An embedding model outputs a fixed length array regardless of the input size.
Okay.
So if you feed it a massive document covering, 50 different API endpoints, networking protocols, security guidelines.
The mathematical representation just becomes an average of all those distinct topics.
Exactly. The vector gets completely diluted. It becomes this muddy generic coordinate just resting right in the middle of your vector space.
So if a user searches for a highly specific API parameter that was, buried on page 42 of that document, the overall document's vector isn't going to be geometrically close to the query's vector.
No, the angle is way too wide. The specific meaning is lost in the noise of the rest of the text.
Which brings us to the source notes. They single out chunking as the most underestimated step in the entire retrieval pipeline.
It really is. Data preparation makes or breaks the math.
Yeah.
You have to break the documents down into smaller pieces, say 256 or 512 tokens.
Just so each chunk retains a sharp, highly specific semantic vector.
Right.
But I'm going to push back here on behalf of the engineers listening because, wait, Does the size of the text chunk really matter that much? Shouldn't a powerful AI just figure out the context regardless of where we slice the data?
You would think so, but no. If you arbitrarily chop a document into rigid 512 token blocks, you are inevitably going to slice a crucial sentence right in half.
Ah, okay.
So the setup for a technical solution might be at the end of chunk A, and the actual code snippet resolves at the beginning of chunk B.
Oh, I see. Neither chunk makes sense on its own. Like the phrase "the execution failed" because is completely meaningless without the subsequent error code.
Exactly. If you slice the data poorly, the vectors lose their intended meaning. You're basically sabotaging the entire semantic search before it even begins.
So how do we fix that?
Overlap. Overlap is the engineering solution to that precise problem. You implement a rolling window strategy.
Okay, so if my chunk size is 512 tokens, I might engineer like a 50 token overlap.
Yep. Chunk B doesn't start where chunk A ends. It starts 50 tokens earlier.
Oh, nice.
That overlap acts as the contextual glue, ensuring that ideas spanning the boundary are captured intact in at least one of the resulting vectors.
That makes a ton of sense. It keeps the vector representation sharp and contextually sound, but, and this is a big but, optimize it entirely for meaning creates a massive blind spot, doesn't it?
It does.
Because if our chunks are perfectly tuned for semantic vibes, they ironically become terrible at finding exact meaningless strings.
Yes.
Let's say a developer is debugging an issue and queries an obscure exact error code, like arrow A8086.
Pure semantic search frequently fails that query. Yeah, because the embedding model evaluates Irdomero 80086 and maps its coordinate to the general cluster for, like, network latency issues.
Oh, so it'll successfully retrieve highly relevant documents discussing network timeouts, connection drops, server configs.
But it will completely miss the one obscure forum post containing the exact 8086 error code, because that post's overall semantic meaning wasn't strongly clustered around generic network latency.
So it's being too smart for its own good. It's giving me the vibe of my problem, not the exact serial number I asked for.
Exactly.
So how do we actually retrieve that?
By falling back on traditional engineering. Hybrid search.
Oh, okay.
You don't discard keyword matching just because you have a fancy neural network. You deploy BM25 alongside your vector search.
EM25, right. For anyone rusty, that's the ranking function used by search engines to estimate the relevance of documents to a query. It's essentially the gold standard for exact keyword matching.
Right. So you're combining two completely different methodologies to get the best of both worlds.
I love this. To put a visual to it, it's like dispatching a dream team detective duo to solve a case.
Okay, I like where this is going.
You have the intuitive psychological profiler, right? That's the vector search. They understand human behavior, they read the room, they calculate the semantic angles of the suspect.
Right.
But they are paired with a meticulous forensic accountant, that's BM25. The accountant does not care about the suspect's feelings. They are calculating term frequency inverse document frequency, relentlessly matching exact alphanumeric routing digits.
That is an incredibly accurate analogy, especially when we look at the mechanics of merging their findings, because the profiler and the accountant speak completely different mathematical languages.
Oh, right, because vector search outputs a distance score, like a cosine similarity of maybe 0.89.
Exactly. But BM25 outputs a completely unbounded TF-IDF score based on how rare and frequent a word is, which might be like 45.2.
You cannot simply add those two numbers together. They're on entirely different scales.
You can't. You can't sort a list if the scores mean fundamentally different things.
So how does the architecture actually normalize those scores so they can be ranked together on a single results page?
Through reciprocal rank fusion, or RRF.
Or RF.
Yeah, it's an algorithm that ignores the raw scores entirely and focuses strictly on the ranking order provided by each method.
Oh, clever.
Right. So if the vector search ranks a document as its #1 result, RRF gives it a high fusion score. If BM25 ranks that same document as number 20, it gets a smaller boost.
So RRF just mathematically combines those rank positions to create a unified, normalized list.
Exactly. It merges the deep semantic understanding of the neural network with the exact surgical precision of term frequency.
It is a brilliant architectural pattern. But looking at the compute requirements here, running cosine similarity calculations on millions of dense vectors, simultaneously running BM25, and fusing the ranks. Doing this at search time sounds like a latency nightmare.
It can be.
Right, because in a production environment, if a query takes 3 seconds to return, the user has already abandoned the app.
Which is why scaling this effectively requires isolating the computationally expensive tasks. This is where the nodes pivot to the two-stage pipeline.
Okay, let's get into the two-stage pipeline.
You have a fast bi-encoder for retrieval, followed by a heavier cross-encoder for re-ranking.
Let's break down that mechanism, because a bi-encoder is basically what we've been discussing so far, right? The query and the document are encoded separately.
Yep. We pre-compute all the document vectors offline and store them in a vector database.
So when the search happens, we only have to run the query through the model to get a single vector and then execute a fast geometric distance calculation against the database.
Exactly. The bi-encoder architecture is built entirely for speed and scale. But because the query and the document never actually see each other during the neural network's processing, the model misses subtle linguistic nuances.
Right, it's just approximating relevance based on isolated geometric coordinates.
Yeah.
But wait, if bi-encoders are missing nuance because they process queries and documents in isolation, the logical fix would be processing them together. But a cross-encoder sounds computationally massive. I mean, why don't we just use the cross-encoder from the very beginning if it's the accurate one?
Because a cross-encoder fundamentally changes the operation. Instead of generating two separate vectors, it concatenates the user's query and the document into a single text string.
Wait, really?
Yeah, and passes them through the transformer network together.
It feeds them through simultaneously. That means the self-attention mechanism of the transformer is highly active across the boundary between the query and the document.
That is the crucial differentiator. The attention heads can directly compare every single word in the query to every single word in the document in real time.
Oh, wow.
Yeah. So if the query uses the word bank, the cross-encoder can look deeply at the document's surrounding context to definitively calculate whether the user means a financial institution or the side of a river. The accuracy is astonishing.
But the computational complexity is what, O of n squared?
Yes.
You cannot run a full self-attention transformer model on 1 million enterprise documents at search time. The server would literally catch fire.
Exactly. It does not scale to the entire database.
Yeah.
Hence, the two-stage pipeline. Stage 1. You deploy your fast bi-encoder and your BM25 keyword search to instantly sift through the million documents.
It acts as a massive funnel.
Right. Grabbing a rough but generally relevant shortlist of, say, the top 100 results.
Ah, so the blunt instrument narrows the haystack.
Precisely. Then, stage 2. You take just those 100 shortlisted documents and you pass them to the cross-encoder.
Because the cross-encoder actually has the processing bandwidth to run its deep self-attention analysis on a tiny batch of 100.
Exactly. It reevaluates and meticulously re-ranks that tiny subset to pick the absolute most relevant, highly nuanced results to present to the user.
That is so smart. You leverage the pre-computed speed of the bi-encoder to handle the scale, and you deploy the heavy cross-encoder solely for final mile precision.
That elegant balancing of computational resources is really what separates a toy application from an enterprise-grade backend.
Absolutely. But designing the architecture is really only half the battle, isn't it? Because the notes issue a very direct warning for engineers at this phase.
Oh yeah, they say to avoid demo-driven development.
Demo-driven development. Let's paint a picture of this trap because we have all seen it. You build out the two-stage pipeline, you tweak your chunk sizes, you run a handful of test queries that you manually selected, and the results look incredible.
Always do.
So you pull the engineering manager over, run a quick 5-minute demo. It feels like magic. Everyone signs off, you push to production, and it immediately fractures under the weight of actual unpredictable user behavior.
It's a classic trap. Generative AI naturally demos flawlessly. The output looks sophisticated by default, which really masks underlying retrieval failures.
Yeah.
Relying on vibes to evaluate a search engine is an engineering anti-pattern. Validating this architecture requires stepping away from the subjective interface and leaning into rigorous, traditional quantitative metrics over a dedicated test set.
And the architecture notes specifically mandate 3 mathematical metrics for this evaluation: precision, recall, and MRR. Let's unpack the math behind them, starting with precision, which is relatively straightforward. Out of all the documents the pipeline returned to the user, what percentage were actually relevant to the query?
Right. And then recall measures the inverse of that blind spot. Out of all the genuinely relevant documents that exist in your entire database, what percentage did your pipeline actually manage to retrieve?
So a system might have perfect precision because it only returns 1 document, and that document is correct. But its recall is terrible because it missed 20 other vital files.
Exactly. Balancing precision and recall is standard.
Yeah.
But MRR, mean reciprocal rank, is where the evaluation gets really surgical about user experience.
How so?
Well, MRR mathematically forces you to care about the exact order of your results, not just whether the document was found somewhere on page 3.
Right, because nobody clicks to page 3.
Exactly. The calculation behind MRR is vital for developers to understand. You evaluate the rank position of the first relevant document returned.
Okay.
If the perfect answer is the absolute first result, the reciprocal rank is 1 divided by 1, a perfect score of 1. If the first relevant document is buried in the second position, the score halves to 0.5, third position, 0.33.
Wow. So it aggressively penalizes burying the lead.
Very aggressively.
And you take the average of these reciprocal ranks across thousands of test queries to get your mean reciprocal rank. This fundamentally changes how a developer tunes the system.
It has to.
Because if you decide to change your role and overlap window from 50 tokens to 100 tokens, or if you adjust the RRF weights between your BM25 accountant and your vector profiler, you don't just squint at a few search results and guess if it feels better. You look at the delta in your MRR score.
Exactly. You engineer the intelligence, you don't guess at it.
Yeah.
Establishing a golden data set of queries paired with known correct document IDs allows you to run automated mathematical evaluations every single time you tweak the pipeline.
It basically brings the discipline of continuous integration to semantic search.
It really does.
Just look at the mechanical journey required just to retrieve a document intelligently.
Oh.
I mean, we moved from the rigid, exact match deterministic databases to plotting text in multidimensional geometric space.
Yeah.
We engineered rolling token overlaps to preserve semantic continuity during chunking. We fused the TF-IDF math of BM25 with vector distance scores using reciprocal rank fusion.
And we balanced the computational load.
Right, by funneling fast bi-encoders into heavy self-attention cross-encoders. And we grounded all of that magic in the cold, hard math of mean reciprocal rank.
Deconstructing it component by component reveals that the magic of AI is really just an incredibly dense stack of logical, well-understood engineering decisions.
It's all just math and architecture at the end of the day, and the notes we are exploring indicate this is just the foundation.
Oh, absolutely.
Next time on the deep dive, we are taking this optimized retrieval pipeline to the next frontier. We're going to examine how developers combine this advanced semantic search with text generation models to construct autonomous AI agents.
That's where it gets wild.
Yeah, we are moving from applications that passively return documents to entities capable of chaining actions, utilizing external APIs, and autonomously solving multi-step engineering problems.
Because connecting a semantic reasoning engine to actual tool use completely redefines the scope of what software can execute.
It is going to be a fascinating breakdown. But as we wrap up this session, I want to leave you with something to think about while you write your next query. We started by contrasting the rigidity of a SQL database with the intuitive, intent-driven mechanics of semantic search. But if we are rapidly approaching an architecture where AI agents can utilize tools and execute actions based on that retrieved data, well, at what point does search stop being a passive retrieval mechanism we query and start becoming an active participant that goes out and solves the underlying problem before you have even finished typing?
The line between retrieving an answer and executing a solution is disappearing entirely.
The deterministic safety of the exact match database is gone, but what we are building in its place is incredibly powerful. Thanks for digging into the architecture with us tonight. Keep building.